Hi everyone, this is a reflection video for POGIL 7, our exercise that dealt with activity coefficients and the concept of activity in chemical equilibrium. This mainly dealt with chapters 7-2 and 7-3 in your textbook, but also drew some from 7-1. So I'm going to give you a little reflection video, hopefully summarizing what I would hope is the sort of take-home message from this exercise. And then I'm going to go through a practice problem. Might be the type of thing you might see in a quiz or exam in the future, but just to sort of show you how to apply what we learned in the class today. So this is our POGIL reflection video for the exercise we completed on the 27th of September. So this dealt with chemical equilibrium. In particular, we're talking about activities and the activity coefficients and their effects on equilibrium. And so for a generic equilibrium, which we've described before, where you have something like A plus B goes to C and D, right? What we traditionally thought was, what we traditionally said was that K equals concentration of A, right? Oops, that's not right. It's products over reactants. So what I meant was the concentration of C times the concentration of D, both your products, over your reactants. And we used the example in class. We were focusing on KSP, where there really were there was nothing on the denominator here. We were just focusing on the numerator. And that was just to simplify sort of the problems, but it does apply to the whole system here. And so what we found was that, from our previous experience from POGIL 6, we saw that the ionic strength of a solution, so basically the ionic atmosphere that the molecules, the ions are floating in, can affect the effective concentration, can affect equilibrium. And so today we started to look at, or today and Wednesday we started to look at how we describe this, and this is described through this concept of activity. So we replace essentially our concentrations with the activities, and then the activities, we define them as the concentration of a species times a sort of modifier here, which is what we call an activity coefficient. And so that just shows what this is here. So this is your activity coefficient. And this activity coefficient is a way to basically describe the effective concentration of your species in solution, because what we say is that by definition the equilibrium constants are constant at a constant temperature and pressure, and so this is what we call our activity, right? And so this activity coefficient allows us to relate the effective concentration to the actual concentration. And so the activity coefficients, we talked a little bit about where these numbers come from the Bi-Huckel theory. And there's a couple things I want to point out. One is you'll notice that ionic strength plays a role, and this makes sense. So if we look at the table here, we see this is a table of activity coefficients of different ions, and here's the ionic strength. And you see basically as we increase the ionic strength, the size of the activity coefficient decreases, and you notice that as we decrease the ionic strength, the activity coefficient approaches 1. And so if you look at it this way, right, as this approaches 1, right, then our activity is just our concentration. And then we can go back to our plain old expression for equilibrium, because we can ignore activity at that part. So that's at low ionic strengths, but at high ionic strengths you see that this diverges from 1. Okay, and what I told you is that basically the assumptions that we make when it comes to activity really break down once we get above 0.1 molar. So basically this table only goes up that high. And what you see is not always the case, but in many cases the lower concentrations below 0.001, we are approaching 1. We're not exactly at 1, but we're pretty close to it. And so lots of times we don't go lower than that. But if you need to calculate it more exactly, you can use this equation right here. Right, and this, again, this uses the ionic strength. That's one factor I wanted to mention. The other one was charge here. And so this is just the charge on your ion. So you can see from this table we have charge plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. And you can see if you look down one of these tables here that in general, right, you'll see that as you increase charge, you have a really strong effect on your activity coefficients. These ones with plus or minus 4, right? So your effective concentration here at 0.001 molar solution is going to be, we're looking at around 0.5 of what our actual concentration is. So it plays a really strong role. The other thing that I wanted to note, which we haven't talked about before, is this is our hydrated ion size. And what I said was, right, as we decrease our hydrated ion size, this is shows a picture of that. As we decrease our hydrated ion size, the charges that are in solution, so if you look at an example, let's look at a smaller one here. Let's say let's compare our lithium to our potassium here. But the charges can better sort of hide, right, from the ionic strength. The ionic atmosphere can better hide this ion in solution. So essentially the effects of activity of ionic strength, the ionic atmosphere, are greater the smaller your ion is. And you see that from this table, that it's not as prevalent at low ionic strengths, but at high ionic strengths you start to see it a little more, that these ones with with a larger hydrated ion radius, here is alpha, have higher activity coefficients that are closer to 1, whereas as you shrink the ions down, this activity coefficient diverges further from 1. Okay, so those are the three characteristics that really come into play when we're thinking about this activity coefficient. And so here's this table. I didn't mention this before, but this comes straight out of your book. This shows you sort of in a graphic form the effective charge on activity coefficient at different ionic strengths. Okay, so I just want to run through a quick practice problem to sort of show you the type of thing that you might be asked to do to apply what we know about activity and activity coefficients. So in this example, the question is, what is the pH of a solution that's containing 0.1 molar NaCl? Okay, so our sodium chloride here we know is a strong electrolyte, meaning it completely dissociates into Na plus and Cl minus, right? Because this is 0.1 molar, then we know that these are both equal to each other, so these both equal 0.100 molar. All right, so now that we're talking about a high ionic strength solution here, we need to think about activity. And so when we're defining pH, pH is not simply defined as a negative log of the concentration of our H+, but rather we're going to be talking about the activity of our H+. And that is equal to negative log of our proton concentration here times the activity coefficient on that. Okay, and so so the question is, what we need to know is what is, so you'll see this is a 0.1 molar solution. So as we know from our equation, this is really highly dependent on ionic strength, and so we need to figure out what that ionic strength is. And so since we know that both the sodium and the chloride are 0.1 molar, we need to calculate ionic strength. And if you recall from POGIL 6, ionic strength is equal to 1/2 the sum of all the charges, or all the concentrations, times all the charges squared. So in this case, this equals 1/2 of our sodium concentration, which is just 0.100 molar, times the charge squared, which is just 1. Put a bracket around here, plus 0.100 molar times 1 squared. And this is from your chloride. So just to emphasize that, this is our sodium, and this is our chloride. Well, you see, if you finish this calculation, you'll find that our ionic strength this case just equals 0.100 molar. Okay. So fortunately, that's a nice number for us to work with because we have a table value for that. And so if we go back and we look at our table, we can find our H plus and the activity coefficient at ionic strength 0.1 molar is 0.083. So using this equation, we know that if we want to figure out our H plus concentration, we can use our KW relationship. So KW equals 1.00 times 10 to the minus 14. That equals, right, because we're taking account for activity, our H plus times the activity coefficient in the H plus times our hydroxide times the activity coefficient on the hydroxide. And so we know that every time you create an H plus in this situation, you're also creating an OH minus, so we can call this X, this X. So we can rewrite this expression as being X squared times the activity coefficients. Okay. So now we just need to figure out what our activity coefficients do. See if we divide, I'll rewrite this down here. So we have KW, which equals 1.00 times 10 to the minus 14. Right, if we divide that by these activity coefficients, we get our activity coefficient for our H plus, our activity coefficient for our hydroxide. This is going to equal X squared. So we can just go back to our table and we find our H plus is here and our hydroxide is all the way down here, so 0.76. Okay, so we plug those values in, we get, this is 0.76, this is 0.830, I'm just going to 0, 0. So we solve for X, which ends up being 1.25 times 10 to the minus 7. Alright, so this X is our hydroxide concentration, but it's also, so now we can solve for pH, which we remember from our previous equation, was negative log of H plus times the activity coefficient of H plus. We just plug in these values we just found, so this is negative log of 1.25 times 10 to the minus 7 times our activity coefficient, which is 0.830. And this ends up giving us our pH, which equals to 6.98. Alright, so you can see when we count for the activity effects of sodium chloride, we do alter our pH. Not very much, but there's a noticeable effect. Alright, so I'm going to follow this up with another video which shows you an easier way to calculate activity coefficients so you don't have to use that big equation. And so I'll see you soon.